Yo, chemistry, part two.
All right, let's talk about chemistry. Yeah. Okay, so radioactive decay. You guys learned about this last year in seventh grade when we talked about absolute dating and how scientists found how old layers of rocks were based on radioactive dating on intrusive or igneous rock, and then also on carbon dating on fossils, okay, to kind of figure out relatively how old that layer is. So, radioactive decay, I just wanted to point out because it really ties in nice with the chemistry here. So, radioactive decay is a radioactive atoms produce energy and particles from the nuclei. The identity of these atoms changes because the number of protons changes. And remember, I said the number of protons changes. Yeah, that's right. That element, it's no longer that element, and this does occur. It occurs at a steady rate, which is that is a characteristic of a particular isotope. All right. So what happens is that it's an isotope, and then what happens is actually it'll start to lose even its protons. Okay. And they go through what is known as a half-life, which is the amount of time it takes for one half of the atoms, in particular, sample of to decay. All right. So, for example, uranium. All right. So, uranium. If you look on the table, I believe that's 92. So let's look for. Trying to find it here. Oh. Uh, yep, I'm right. Uranium, okay. Which is, the atomic number is 92. Actually, it is a radioactive element, okay, which I forgot you guys color that too. And what happens is it'll actually change into lead, okay, so it'll actually lose its protons, all right, and it'll turn into Pb, all right, which is up here 82, so it loses 10 protons, all right. Um, then once it's done that, it turns into lead, and it takes about 704 million years for that to occur. So if you look at this picture here, so half-life, the green is the percentage of original unstable, okay, and then if you look over here, the blue indicates the percentage that the element has changed. Okay, so they look at a sample of uranium, and then once it's went through one half-life, so what's half of 100? Okay, that's 50. What's half of 50? 25. Half of 25, 12.25. Half of 12, I'm sorry, 12.5. Half of that is 6.25. Okay, and so for it to go through every half-life, it takes 704 million years. And so we do know here in Missouri, we were at one point, it was uranium, and it has decayed into lead, which we know we live in the lead belt, which is where we actually mine galena for lead. All right, so we know it's at least 704 million years here. Okay, so look at here the chemical formulas. The chemical formula uses chemical symbols to represent the atoms, the elements, and their ratios that there are. Okay, so for example, if here these are called subscripts. Okay, so we have one carbon atom and two oxygen atoms, two hydrogen atoms and one oxygen, one nitrogen and three hydrogen. Okay, so it's just a way that you understand how many atoms of that element are in this actual bond. Okay. Okay, so ions, as we talked before, is just a charged atom. Remember, it just means that the protons and electrons are different numbers. Okay, and the fewer electrons pull per shell, the less energy it has. So if it's smaller, it's going to have less energy. If it's bigger, it's going to have more pull. Okay, so I'm going to show you here what I mean about that. So the ionic bonding is bonding that involves a transfer of electrons. And as I said, the ultimate goal of all atoms in the whole wide world is to be full, fat, and happy. And that's why the noble gases are not very reactive, because they're already full of fat and happy. They don't want to be messing around with these peasants down here. Oh, heck no. Okay. All right, so if you look here, when we talk about ionic bonding, this only occurs between a metal and a nonmetal. So you have to look at your periodic table and look at the color you colored for metal and the nonmetal. Okay, so some great examples here is sodium chloride, magnesium oxide. Okay, so those are two really good examples here. So let me go ahead and show you how to draw these out, because you're going to be responsible for this in just a little bit. Okay, so let's go ahead and take magnesium. Okay, magnesium is 12 and it is actually 24. Okay, so that's easy, right? Okay, so let's go ahead and draw this out. All right, so we're going to go ahead and use magnesium. Okay, so magnesium, we just said it was 12, right? 12P, 12N, nice 12. All right, so let's go back and look at the periodic table here. All right, so the first thing we got to do is, oh, it's got 3 shells, because that's what the period number is. So let's go ahead and draw that. Okay, 1, 2, 3. All right. Now, how many are we going to have in the outer shell here? Well, if we look here, Mrs. LaRue, it's in group 2. So we're going to have 2 in the last shell. That's correct. So let's get those 2 electrons there. 1, 2. All right, so let's go ahead and work in out. So what's the most we can have in the first shell? Good job, 2. What about the next one? 8, 2, 3, 4, 5, 6, 7, 8. Okay, and then the last, we're supposed to have 2. So 2 plus 8 is 10, plus 2 is 12. That is correct, because this is stable as of right now. So let's go ahead and check out oxygen. All right, so let's go back and look at that. So oxygen right here is 16 and 8. It is in period 2, and it does have 6 electrons. So let's go ahead and check that out. All right, so oh, I really made that smaller, didn't I? Okay, so let's go ahead and draw this out. Alright, so we got 8 protons, 8 neutrons. Alright, and we said it was in group 2. Okay, and we're going to have 6. 1, 2, 3, 4, 5, 6. And the most you can have in the first one is 2. Okay, so you don't really look at size, you look at which is more energy efficient. So look at these two, okay? Would it make more sense for oxygen right here to lose all 6 and go to magnesium? Or would it be more energy efficient, make more sense for magnesium to lose the 2 and come over here to oxygen? That's correct. So what's going to happen is these electrons will then go over here once they get close together. Alright, so now oxygen's full, fat, and happy. And then check this out. Now we can erase the outer shell here. Alright, and then what happens? Okay, now we have magnesium. Since it lost those 2 negative nellies, now it becomes positive 2. And then oxygen here becomes a negative 2 because it actually gained 2 negative electrons. Okay, so that's what happens. So the 2 went over here, lost its outer energy shell, gained the 2, full, fat, and happy, because now we have 8 in the last one. Okay, all right. Now, your ionic bonds are very unhealthy bonds. They're very, it's just like always give, and so that other person just takes. Very, very unhealthy relationship. That's a counseling. Okay. Now, if you look at this chart here, you will see in group 1, there's only 1. So let's look at this chart and tell me what groups are MFEO. Made for each other. Okay, so let's go ahead and check it out. MFEO. All right, yes, groups 1 and 7, they go. because that wants to give up one, and that one becomes full, fat, and happy. Okay, groups 2. Very good. 6. Group 3. Very good. They all add up to 8, don't they? Because 8 is the magic number. All right, what about 4? Very good. So those are the groups that are M, F, E, O. So 1 goes to 7. Okay. Then 2 goes to 6. And then 3 goes to 5. And 4 goes to 4. Okay. Okay, so when you talk about ionic bonds, we're talking about naming them. All right, so for example, if you have, list the name of the metal. Okay, so you always start with the metal, so Na equals sodium. Then when you change the ending of the non-metal, you always change it to IDE. So for example, chlorine changes to chloride. So when you put the two names together, then it would be called sodium chloride. So the non-metal always changes to an IDE. Okay, so we will practice this when we're in class. All right, and that only happens with ionic bonds because it's very unhealthy. And it's like those marriages, you know, you give up your last name, you know what I'm saying, girls? Wow, yeah, and then, yeah, we'll talk about that later. All right, now on your own right now, I want you to go ahead and complete this. Draw a picture of each of the following and show which element gives away their electrons to the other. So I want you to draw these two, and I also want you to draw these two in the flip section in your notebook. Go ahead and do that now, please. All right, so covalent bonds. So covalent bonding, it's a bonding of atoms in which elements are shared. Very, very, very healthy, very good, very complementary kind of a relationship. Okay, so this only happens between two nonmetals. All right, now I wanted to point out to you, I know hydrogen was actually in a metal column, but it's actually considered a nonmetal. And when we get to class, I'll explain to you why that is. Okay, but do realize hydrogen is a nonmetal. And nonmetals are they're terrible conductors. Terrible. Now, metallic bonds are like the bonds from the 60s, man. It's all carefree. It's all good. We all share. We all care. We're all together. And metallic bond is formed by atoms of metals in which the outer electrons of the atoms form this cloud. They call it the sea of electrons. And they're shared equally in all directions because everybody's together. We're in this together. And that forms metallic bonds. Now, metals are elements that give up electrons easily. And the atoms of metals form metallic bonds because they're so free and loose, man. They're the 60s. We can do this. All right. So it is so free that you can actually, that you can stretch it without breaking it. It's very malleable, meaning that you can actually hammer it, flatten it. Okay, and they're great conductors because they allow anything through because it's such a loose and free relationship. They all care because they are the sea of electrons. There's so much space in between, they can do that. So they're fabulous conductors. All right, so for tomorrow, I want this in your notebook, okay? I want you to complete the filing. I want you to draw the atoms of lithium and fluorine. Okay, H2O, remember hydrogen is a nonmetal, and lithium plus beryllium. I want you to draw the atoms, the protons, neutrons, electrons. Make sure you draw all those, and also make sure you name what bond it is, ionic, covalent, or metallic. Bring it to class tomorrow, and let's see how you did.